All right, here we are for another AP biology video. In Unit 1, we started with this idea that cells could have arisen from non-living chemicals in the primordial soup or the primordial ooze. And we learned that at some point a cell membrane needed to develop, needed to evolve. Because you need a barrier, you need a body, you need a way to keep outside stuff out and inside stuff in. And then we moved past that to the idea that you also need to get things in and out, right? And so at some point in there, you start to realize that in order for all this to work, you need energy, right? Now, the first primitive cells would have just been these bubbles, right? Like, where are they going to get their energy? So the energy chemical reactions that we would call metabolism had to also be evolving probably at the same time, maybe. It's hard to say. We'll probably never know exactly which one came first or how it actually happened. But in any case, you need energy. And so in this video, we're going to talk about energy and a little bit more about the specifics of how energy works in a living system, or the big picture ideas, actually. Some of the stuff is going to get a little bit detailed, but a lot of it is beyond what you would be tested on. It's just stuff that helps you to frame the energy discussions we'll have in further videos. So the idea is there's stuff called free energy, the ability to do work, right? In this case, work would be to stay alive, right? We need a bunch of chemical reactions to happen to keep us alive, and that means the chemical reactions need to release or harness free energy, right? And so here is a mathematical formula for free energy. The G stands for Gibbs free energy, and Gibbs must have been some dude who developed this formula. Now, the energy is related to two different ideas. The first one is the H, the delta H, and this is, the triangle means change in. Delta also, something about the Greek letter delta, maybe that looks like a triangle. I forget exactly, but we say delta H, the change in H, and H is called enthalpy. Maybe you were thinking this was going to say heat, and that's kind of what it is. Enthalpy is a word that I know I never heard until I got to this kind of stuff in chemistry and biology in college. Enthalpy means total energy, which again is kind of like heat. But then you look over here and you notice that there's already a temperature thing over here, right? And so this is where you have to maybe understand that energy and heat are not exactly the same as temperature. Specifically, temperature is a measure of the average kinetic energy of the particles inside of the measuring device, right? And so it's not exactly the same thing as energy. And one other way to look at this would be to check out the phase change graph of water. We kind of looked at this once already when we were doing water properties, but it shows energy on the x-axis increasing towards the right as usual, and then temperature on the y-axis. And at first, it's what you would think, that when you start with ice and you start to add energy, the temperature goes up, right? But then you hit this spot right here called melting, right? Where you add energy, but temperature doesn't go up, right? And so right there, you have the idea that temperature and energy are not the same. Because in this case, the melting part is more about breaking hydrogen bonds rather than making the molecules bounce around more. And again, temperature is actually just how fast, how much are they bouncing around and hitting the walls of, say, the thermometer or whatnot, right? So here, and also in the evaporation part, and that's of course that's a lot bigger and easier to see. I probably got to start there. That when you add energy, it doesn't make it get any hotter, right? Because here, especially, the water molecules are moving as fast as they can, but they can't break away from the hydrogen with the hydrogen bonds. Once they finally break away, they can bounce even faster and with more energy, and they get hotter. But again, total energy is something a little bit different than temperature. So in any case, we have energy over here. And then over here, we have temperature times this thing called S. And S is entropy. Entropy is disorder. It's chaos, basically, right? And so this is an interesting part of the universe. Somebody, I forget exactly who, discovered the laws of thermodynamics, and that says that every time there's an energy transfer, that entropy should increase, right? And so chaos should always be increasing according to this. But then on the other side, you have the other term, the energy, right? And so this sets up this battle basically between energy and chaos, right? And this is a very important idea, considering that living systems are extremely ordered systems, right? Chaos would be bad inside of your cells, right? If things didn't behave exactly the way they're supposed to behave, exactly when we need them to, then we're dead, right? How do you beat that then, right? If the universe says that we always have to have chaos, in the end, we need energy, right? And so this is just a fancy way of saying you need to eat in order to live, because we need a constant free energy input, or we will lose order, or we won't have the energy required to live, right? And so in the end, we need processes that are going to release energy so that we can decrease entropy, right? This is basically the physics definition of being alive, is maintaining your energy long enough to keep the entropy at bay until you don't have enough energy to do that, and then the story's over. So here's the way we're going to look at it quite often, is that we have this kind of graph of a chemical reaction where you have your reactants over on the left, and then you have time on the bottom, and then of course your reactants become products. And so in this particular case, the reactants have more energy in them. For example, one molecule of glucose, which has a lot of carbon, hydrogen bonds. So there's a lot of energy stored in here. That's going to then turn into, during cellular respiration, 6 carbon dioxides, right? There are no carbon or carbon-hydrogen bonds in the carbon dioxide, very little energy in each bond. But not just that, the glucose is very ordered. It is big and it has a very particular structure. Meanwhile, the CO2 molecules are all simple. There's only 2 bonds, and there's 6 of them instead of just 1, right? And so this is called an exergonic reaction, that when you break all these bonds that have tons of energy in them, we will release energy and make products that have very little energy left in them. And then the amount that you get here, that's, as you can see, is the delta G. We'll talk more about it's a down, it's a negative. That's a weird thing, but we'll get there. On the other side of this, you have something called an endergonic reaction. This is going to require energy because in this case, your reactants, there we go, 6 carbon dioxides have very little energy in them. And they're very chaotic because there's 6 of them to bounce around as compared to what you want to make, which is a glucose, right? And this is going to means we have to put in energy. And again, this has to do with your delta G that we'll get to. But the bigger idea here is that chaos can become ordered if you put enough energy in there, right? And so there we go. Endergonic and exergonic are words you'll see, not tested too many times, but we are going to go over them a little bit more as we go along. Now, these are 2 very big things that we will talk about, cellular respiration and photosynthesis, in their own whole big sections. But right now, there's 2 other ways to look at this. And this is the idea that there are some reactions that will release energy because they digest things, they break them down, or we could use energy to make things for synthesis, right? And so these words, hydrolysis and dehydration, I'll go explain them right now. So here's something that I alluded to in the first unit, and we really need to understand it better now, because now we are going to start to see these things called polymers. In fact, you already watched a video that's about proteins, which is all about proteins are polymers. And so there's all these biological molecules that we need to take smaller things called monomers and connect them together to make polymers. So here we have already connected 3, and they're showing you connecting the 4th one onto this chain, and then we would put a 5th one and a 6th one, and however many of them that you need, which can be in the hundreds sometimes, right? But the idea is that this is going to decrease entropy because we're taking 2 things and putting it into one thing, right? So we're already making the chaos smaller. This requires energy. And it also has this name called dehydration synthesis, because you'll notice that we're going to take an H and an OH. So there's 2 H's and an O, H2O. We're going to remove a water. And then the chemicals that are linked here are going to be able to be connected to the chemicals here. So let's take a look at some of these examples. This is the one that you just saw in the good old protein video, which is to join amino acids. And again, here's our carboxyl group of 1 amino acid, and it has an OH part in it. And then the amino group over here, of course, has an H just sitting here. And so if we take away these 2 atoms and they go off to form water, we get the C that was connected here is now all the way connected to the N. And there we go, it's our CN peptide bond. Now that bond required energy to make. We have to put in 2 to 4 kilocalories per mole to join those amino acids, right? It has an energy cost to it. To make carbohydrates, complex carbohydrates like sucrose, which is made from a glucose and a fructose. These are 2 monomers that we're going to join to make a polymer, a short one. Technically it would be a dimer, but in any case, we are going to take away the water. Here's our dehydration synthesis. And then the carbon that was connected to the O here is going to be connected to the oxygen that used to be connected to the H, right? There we go. We can see it right there. This requires between 3 and 4 kilocalories per mole to join them. Here's how we make our DNA. This one's a little bit harder to make. You have to put more energy in because this phosphate does not really like to be smushed up in here with the other molecules, because this is a big negatively charged polar thing, and it takes up a lot of space, chemically speaking. So you got to really shove it in there. But there we go. We get our dehydration synthesis to make the covalent bonds, something that I should have mentioned earlier, but these are all covalent bonds that we're making, and that costs energy. We already talked about making lipids. These aren't really polymers though, remember? Like this is like the biggest kind of polymer you can get, whereas you take 3 fatty acids and link it to the glycerol to make a triglyceride. And I don't remember exactly why, but I didn't find the energy required, but it definitely requires energy to do that, right? And so we're going to have part of the free energy usage would be towards making all these things that we need to make. But then we have the opposite. Sometimes we need to break things, oftentimes the same thing that we already made, because now it'd be useful to break it apart again for whatever reason, right? So here's the generic idea that we have the 4 4 parts of the polymer. They're all monomers that make the polymer. And then we inject the water back in. It's interesting the way that this arrow is drawn, like you're putting it into here, right? Up into the bond. And now we have separated the monomers. This is going to release energy. And actually, the way the chemical bonds work, it's exactly the same going forward or backwards. So you would get back everything that you put in, minus probably a little bit of heat, because nothing is completely efficient in real life. But we'll get to the heat thing later. And so there we have it. The basic idea of living things is that you stay alive by constantly making and breaking chemical bonds by using and or releasing energy, right? And so now we'll get into some of the more, in later videos, we'll get into more specifics about where is all the energy going to go and what are we going to do.